Let's go through activity 10. So I'm going to load up all of these libraries that we need for this assignment. If you don't have one, you can always install .packages. That one is preferably down here on the console so that no sort of errors get involved when it gets embedded in there, and we'll be good to go. So within the library reg class, we have a data set about abalone, which are sea creatures that people eat. And we're going to try to do some predictive analytics, trying to figure out a model to describe the meat weight that is inside these abalone. So what we're going to do is we're going to first scale the observations in the abalone data frame. They're all numerical. And this will be important for a lot of different model building procedures that we use. They care that each variable is more or less on the same scale. So we need to make sure that each variable has a mean of 0 and a standard deviation of 1. All right, so let's go ahead and split the data into training and holdout here using our favorite random number seed, but this time with a 50-50 split between training and holdout. So we can set the training data to be the train rows and the holdout to be everything but the ones selected for training. So I'll go ahead and run that whole chunk, and let's move on to number 2, where we're asked to explore visually some of these relationships. So we're asked to make a scatterplot matrix, and what we're going to do is focus in on meat weight. Meat weight twiddle dot will make a scatterplot matrix of all of the variables in the data frame, but having meat weight be the top row. So that we can focus in on that. That's what we're trying to predict. All right, so looking at the relationships between meat weight and these other predictor variables, we see some nonlinearities with some of these predictors. So, all right, we'd like to develop a model that can learn this nonlinearity and come up with some sort of effective way to make predictions on new individuals. All right, well, let's start out by trying a neural network. So what we're going to do is fit the neural network on the training data with one hidden layer that contains 2 neurons. All right, so we're going to load up the library neural net package, and we're going to put the syntax for our neural network. All right, so what we have to do is to say what we're trying to predict, meat weight, twiddle, and then all of our predictors. Now, if it was just twiddle dot, that would be all the predictor variables in the data. But in this case, I want everything but whole weight to be a predictor. So I actually have to manually type out all of the predictors I'm using separated by plus signs. So that's my formula. We're doing this on the training data, and we want to make sure to have 2 neurons in that hidden layer. And then also we're going to want to add the argument linear output equals true because we're doing regression. We're not doing classification. All right, so I can do the seed and the neural network command at once. And then I can cross my fingers and hope that I can make a plot of this because we like to see what this model is doing. All right, so when I do the plot command, good, it worked. We get a plot up here that describes how the neural network is functioning. Now, how is this working? Well, we have 5 different predictor variables, and those get input into the input layer of the neural network. Now, what happens from here is that the model constructs weighted sums of the predictor variables, and these are fed into the neurons into the hidden layer. So we have 2 neurons in our hidden layer. What would be the weighted sum of the predictor variables going into this top neuron? Well, we would have first the bias term, basically an intercept or a constant that we're adding to the weighted sum, and that would be minus 0.27. So what's going into this neuron is minus 0.27 minus 0.54 times length plus 0.068 times diameter minus 0.13 times height minus 0.36 times shell weight plus 0.05 times rings. Those are the numbers above the arrows, all pointing to this neuron. So this neuron is going to deal with that weighted sum. The bottom neuron is going to work with a different weighted sum. So we can look and we can verify that the weighted sums provided in part C are the correct ones. And indeed they are after a little bit of rounding. All right, so what happens in this hidden layer? Well, both of these neurons take their weighted sums and transform it, run it through some sort of activation function, typically the logistic function. So if z happens to be the value of our weighted sum, it's going to calculate the e raised to the z power over the quantity 1 plus e raised to the z. And that's what's going to come out of each of the hidden layer neurons. And those outputs are going to be recombined in a different weighted sum. The weights of that sum are given by the numbers above the arrows. We would basically take 5.2 minus 3.8 times what's coming out of this neuron minus 3.7 times what's coming out of this neuron. And that's going to be our prediction for meat weights, potentially with another logistic transformation along the way, depending on how the neural network is set up. So, all right, fairly simple model, just one hidden layer, two neurons, but there's still a lot of parameters, a lot of weights that have to be estimated. How many total? Well, this weighted sum, what's going into this neuron, requires 6 weights, the 5 predictor variables in the bias term. The weights all have to be estimated. And same thing for the bottom neuron. So we have 6 plus 6, which is 12. Then the outputs of those two neurons get weighted together along with a bias term to make the final prediction. So we're going to have a total of 15 different parameters that our data has to estimate. All right, well, we've already fit this neural network model. Let's go ahead and make predictions and kind of see how they work. All right, so to make predictions, what we're going to do is use the compute command. The predict command doesn't work well with objects created from neural net. And we can just run the code as is. Now, normally, the second argument will just be holdouts. But in this case, what we're doing is we're taking out the 4th and 5th columns because the 4th and 5th columns contain, number 1, our y variable, the thing we're trying to predict, the meat weights, and a variable that we were excluding. So I guess I misspoke slightly. Instead of just holdout by itself, it would always be holdout, bracket, comma, then minus some number, wherever our y variable was. That's just the way that you have to set something up for compute to work. All right, so let's get our predictions on the holdout sample, and let's see how well are we doing predictions. I'm going to start out with the second one here, the scatter plot with the predictions versus the actual values. Let's have as our y variable the vertical axis, the observed values, and let's have our x-axis be the predicted values. And we see that they're matching up pretty well. I can add a diagonal line for perfect correspondence, a slope of 0, or a slope of 1, intercept of 0. And we see that, yeah, our predictions are, on average, correct. There's just some spread about the actual values from where we're predicting. We definitely see some heteroscedasticity where the size of the error is getting bigger for larger values of the meat weight. All right, how is this neural network treating the relationship between the meat weight and the length of the abalone? Well, we can make a scatter plot to check that out. So if we make a scatter plot of the predictions as the vertical axis and the holdout $ length as the x-axis, then we can see how the neural network is treating the relationship between the length and the value of the meat weight. Or I think I want to reverse this. I want to have, nope, yes. I'll reverse this back so that we actually have the predicted values, how the meat weight is supposed to be according to the model versus our x variable, the length here. And just going back a few plots, in our scatter plot matrix, we did see that there was nonlinearity in the relationship between the meat weight and the length, basically longer length, bigger meat weights, and that indeed is exactly what our relationship is reproducing, that general behavior. All right, so moving on to number 5, let's try out the support vector machine for doing regression. So we're going to use the default radial basis kernel. So in effect, an infinite number of polynomial terms are being created to help us do the prediction. And what we need to do is we need to tune the gamma parameter of this kernel and then also the cost of making an error. So what we're going to do is to use the tune command that works well with the support vector machine. Now, of course, caret and train will do this. Well, we're going to use tune in this example. And our first argument is going to be the name of the model we're trying to tune, SVM for support vector machine. The second and third arguments need to tell us what the formula of the model is, what we're trying to predict and what we're predicting it from. I'll just borrow that from our neural network. And then we have to say, all right, what parameters do I want to be looking at? So we're going to add in a ranges argument, and we're going to make that a list. And inside that list, we're going to specify that we want values of epsilon that are 0 or 0.5, values of the costs that are 16, 32, and 64, and values of gamma that are equal to 0.005 and 0.01. So what is this epsilon parameter? Well, if you remember the way that support vector machine regression works, is that errors that are small within a value of epsilon or smaller, don't count really as an error. It's only the errors that are bigger than epsilon that the model is trying to minimize. All right, so what parameters look like they're going to work? Well, an epsilon of 0, meaning every error is going to count against the model, a cost of 16, and a gamma of 0.005, and it looks like the best performance was 0.137. So we're going to put that number here, and actually the way I asked for it on Blackboard, it would be the first 3 digits after the decimal point, so just 137. All right, so let's fit the support vector machine with those parameters. I'll borrow the formula and the data argument from up there. And then I need to say that I want to do an epsilon of 0, a cost of 16, and a gamma of 0.005. So we'll fit that support vector machine, and then we'll make predictions on the holdout sample. Now, once again, I need to make sure that I take out the column corresponding to my y variable, which was the 5th column there. And then also, because I didn't use one of the variables as a predictor, I need to take that out from the holdout sample as well. That happened to be the 4th column. All right, so when I make this prediction, I'll get the predicted values, and we can go ahead and get the RMSEs for both the models now that we've tried out so far, and we can see how correlated the predictions are. So our formula for the root mean squared error is taking the square root of the average of the sum of squared errors. So for the neural network, we stored those predictions in predictions.nnet. We'll look at the difference between that and what the actual mean weights were. We'll square that, and that's the value of our root mean squared error. All right, well, does the support vector machine do any better? Let's replace predictions.nnet with svm.predict, our predictions for the support vector machine. And it looks like it's a little bit larger. It looks like that the neural network is slightly more effective at predicting the mean weights of new abalones. All right, so we're just about to do some ensembling, basically combining predictions of different models together. Might it make sense to combine the predictions from both of these models? Well, it makes sense to do so if they have similar accuracies, which they do here, and the predictions are uncorrelated. Basically, they're approaching the problem from a different angle, and so combining the predictions should give a fuller picture of how the relationship works. Let's see what the case is in this scenario. Let's look at the correlation between the predictions from the neural network and the support vector machine. And we see a correlation of 0.996. 1 is as big as it gets. That means they're exactly the same values. So we see that, all right, the predictions coming out of the neural network are pretty much the same as the predictions coming out of the support vector machine. It just so happens the predictions coming out from the neural network are doing a little bit better because its root mean squared error was a little bit lower. So we copy and paste that value up onto Blackboard, and we see that, all right, just combining those two models together probably isn't going to help us out here. So no, the predictions are not independent because the correlation is almost equal to 1, which means they would have a perfect match. All right, so let's just explore this ensembling here, combining the results of lots of different methods. Very computationally intensive, but we're going to be trying out a whole bunch of different models anyway because the no free lunch theorem says that no one model is always going to be the best. So, since we're fitting all those models anyway, why don't we consider combining them together to make an even stronger predictor? So what I've done in number 7 is basically written the code all for you. It's very computationally intensive, and in order for us to all get the same results, it helps if we just use the same bit of code. Any tiny difference is going to change everything else downstream. So the way that we do ensembling, or the way that I like doing it first, is by figuring out what models we should be using in our ensemble. So basically tuning all of the models that we've used so far to figure out the right versions of those models. So here I'm setting up how we're estimating the generalization error of each of the models. And in this case, I'm going to do it with the boot method. Basically create a bootstrap training sample and fit the data on that fit the model on that bootstrap training sample and make predictions on the values that were left out. So we're going to do that for each one of the models to choose the right model to be using. And this is fairly computationally intensive. I'm not going to run it here. All the code here is written for you to give you an example of how you do the tuning when we're predicting an input response. But I have kept track of what the optimal parameters were according to the result of this tuning. Well, at least for the random forest, I didn't have to keep track so much with these others. You can run those for yourself on your own time. But I also was looking at some of the accuracy on the holdout, etc. We're going to skip to where we actually do this ensembling. So we're going to do ensembling by stacking. What that means is we're going to take the output, the predicted values from each one of the models we're looking at, and combine them together in a certain way. And we're going to try this a few different ways. We're going to come up with a weighted sum of the predictions from the different models. So we'll have a weighted sum of our models. And we'll come up with a more sophisticated model to combine the predictions. So we'll use the outputs, the predicted values of each of the models, as predictor variables themselves, as X variables, that we're going to feed into a random forest model, a neural network model. The choice is up to us. So the way that we need to do this is to set up the train control object very specifically so that we create these new predictor variables from the output of the models that we want to fit. So we'll set it up just like this. The key thing is to have save predictions equals final and to create a common set of bootstrap training samples for each model to work with. We'll make sure to set the random number seed. Actually, we need to set the random number seed in 2 places because this is creating at random those bootstrap training samples. In order to get reproducibility, I want to make sure to set the random number seed before I choose how those bootstrap training samples are created. So we'll set the seed one more time, and we're going to go ahead and run this epically long command. Now while it's running, I'll talk about how it works. The command is !list. We need the formula that tells us what we're trying to predict and what we are using to make the predictions. In this case, I'm just doing twiddle dot. We're going to use all the variables at our disposal. And of course, we're fitting this on the training data. Now we're going to consider models root mean squared errors on the holdout sample. So our metric is going to be RMSE. Figure out the estimated generalization error in terms of the RMSE here. So we're going to estimate that generalization error and proceed further by doing what we just saved as the fit control object. And now we need to give it a list of models that we want to consider. A few ways of doing this. Method list, we can pass a vector of just model names that it'll use with the default parameters. So GLM, just vanilla linear regression. There's no parameter that we need to really specify. We just fit a weighted sum of the predictor variables. So that's a perfect one for passing to method list. If we just wanted the defaults with random forest in our part, we could just add those as names in double quotes. If we do want more specific versions of the models though, we're going to add the argument TuneList and then pass it a list of model names and exactly what we want those models to be. So we'll create a list object here, and what we'll say is we want to create a variable called glmnet, exact same name as the method that we're going to be using. Make sure those always correspond, otherwise you're going to get errors. And we're going to say that we want a glmnet method, a regularized regression method, and we're going to give very specific parameters to it. Now in this case, I let it do a little bit of tuning. I'm letting it actually choose between 0 and 0.05 for the alpha parameter, but I'm specifying what the lambda parameter should be. And then I go through the rest of the models I want to consider in the ensemble. In this case, I'm specifying exactly what I want all those parameters to be because I did some pre-tuning ahead of time. I kind of figured out what parameters looked like they were doing well. All right, the command is completed, so let's look at some of the results. We'll run resamples on the name of the object that we saved our command to, and that'll allow us to look at a summary where we can peruse the typical size of the error that each of these models are making on the validation sets that are being generated when we're doing the bootstrap training sample procedure. So we see that some models look like they're more effective than others. The k-nearest neighbors model has a pretty high error on average. Same with the rpart model. It looks like the support vector machine has the lowest average error, at least over these 25 bootstrap training samples. So, all right, looks like support vector machine might be our favorite at this point. We can get a visual kind of guide of what those results look like as well by making a dot plot. Here's the root mean squared errors. It's sorted from biggest down to smallest, so we kind of see how they stack up. And now we can look at whether we should be doing ensembling at all. Are these models different enough that we should be combining their results? We'll look at model core, and the overall guideline is that if we see a number that's bigger than 0.75, those models are probably too similar to really be combining. And we do see that's the case. For instance, the output of the regularized regression model and the support vector machine have a correlation of 0.98. That's super high. They're basically the same values for the predictions, except the support vector machine looks like it happens to be doing a little bit better than the regularized regression. So we probably don't need both in our ensemble. However, GLMnet, the regularized regression, and k-nearest neighbors has a much lower correlation. K-nearest neighbors didn't all that great, but if we did include that in our ensemble, GLMnet and KNN would be fine to put together. So we see a mix of some models that are highly correlated. The random forest and the boosted tree model are pretty highly correlated. The vanilla linear regression, GLM, and the nearest neighbors, not so correlated, so we kind of have a mixed bag. We're just going to go ahead and fit the ensemble with all of these models, but if you're really doing ensembling, you might want to weed out some of these models that we don't really need. All right, so let's do some ensembling, but first let's make a data frame that contains the predicted values of all these different models on the holdout sample so that we can see at the end of the day which one actually ended up doing well. All right, so stacking time, combining the results of the different models. First, let's do this as just a weighted sum of the predictions of each models, and we'll let R figure out basically what the best weights are. So what we'll do is we will set up another train control object. For some of these other combination methods, we'll have to figure out, what random forest model, what value of mtry should we be using. And so we'll set up the train control object. That'll allow us to do that. But when we just want to figure out the weighted sum, well, we'll use method equals GLM to stack these guys together. There's no parameters to really choose. It'll just figure out what the best weights are to apply to each of the models. So we run it, and here are some of the results. The larger the value, the more weight is being applied to that model. So it looks like the support vector machine gets the highest weight. Not too huge of a surprise because it was the one with the lowest overall error. We see some models it's really not even using whatsoever. So the neural network predictions have a weight of 0.008. Just the tiniest bit of information is being incorporated from the neural network. All right, well, let's predict from that model on the holdout sample and add that as a column in our predictions data frame and move on to the random forest. So here we don't know what mtry we should be using, and so that's why defining that stack control, the result of running fit control, is important. We can go ahead and try to combine the outputs of these models, use them as predictor variables themselves to build a random forest model predicting what the actual meat weight was. So this is going through and it's figuring out what value of mtry to use. I didn't give it a grid to search on, so it'll just search on the defaults. And once the command is done running, it'll let me know what random forest looks like it's the most optimal. And I'll go ahead and make a prediction using that optimal value of mtry on the holdout and add that to my predictions data frame. It looks like mtry equals 2 was the way to go. Now finally, let's try combining these models in the context of a support vector machine. The support vector machine was doing the best job at making predictions on new data. It had the lowest estimated generalization error, so maybe the right way to combine these predictions is with the support vector machine, using the outputs of the models as the x variables to feed into a new support vector machine model. So the question is, what support vector machine? We're tuning the sigma and the cost parameters of that support vector machine. It looks like these are the values that are reasonable to choose. And so we can predict from our support vector machine object on the holdout data to our predictions vector, data frame. All right, so moment of truth, we can get the root mean squared error on the holdout sample for each method. I'm going to use a shortcut. This is a command you can reuse again in the future. If you've saved all the predictions for your models in a data frame called predictions, and you've saved your holdout data in a data frame called holdout, all you have to do is change the name of the variable, your y variable. So what this will do is it'll go through and give you the root mean squared errors on the holdout sample from every model under consideration. So the support vector machine of the 8 or 9 original models looks like it has the smallest root mean squared error on the holdout. Do any of our ensemble models beat it? Nope. The weighted sum doesn't beat it. The random forest doesn't beat it. The support vector machine doesn't beat it. So it looks like in this case ensembling is not squeezing out any more information than just one individual model is. In this case, the support vector machine would have been the smartest model to have gone with. So we can look at the actual values versus the predicted values if we just did a weighted sum, which it looks like is the best way if we were going to make an ensemble model, but still just a support vector machine by itself is the way to go. But we do see that the predicted versus actual values are matching up pretty decently.